Hello, good morning. How's everyone doing today?
Good morning, Professor.
Morning, everyone. Okay, so give me 1 second. Let me connect this with my screen share.
How's it going, Professor?
Good. How about yourself?
It's going.
It's going, yes.
No, I said it's going good.
Oh, great. Okay, I thought you said it's going. Well,
No.
that's great to hear. Okay, so when solving physics problems, I encourage you all to think about the physics behind the problems, even though on the surface it may look different, right? For example, an incline problem and a spring problem could all be the same type of physics problem where they use Newton's second law. So if you know how to apply Newton's second law, it doesn't really matter what kind of problem they give you. But sort of to help us practice different scenarios, we did look at different surface features of the problem, such as a problem that has an incline, the problem has a spring on it, a problem that includes multiple objects, where we did in the previous class. So some of the problems use two physics principles. They use dynamics and kinematics. So let's look at a couple questions that is belonging to that particular category. So Newton's second law is not enough. We need also kinematics. So we'll start with this particular clicker question where you have two vehicles and they have different mass. One is twice of the mass of the other. Initially, they're moving with the same speed, same velocity, same direction, speed. And they apply their brakes and they both begin to slide. Noticing that in real life, our car actually operated a little bit differently. Our tire never really stopped rolling, right? Continue to roll. But here, for the simplicity of analysis, we are thinking of them as sliding. That's not what really happened in real life. But if they do start to slide, and you have the same coefficient of kinetic friction for both of the vehicle and the surface, which vehicle stops first? So you can see that which one stops first is a kinematics question. It's asking about the time it takes to stop, right? How much time it takes to stop. So, so think about that. I'll give you a couple minutes to discuss, and then we will come back to vote on this question. So make sure that you take a screenshot before you accept the invitation to join the Zoom breakout rooms. Hello, everyone. I'm joining group 7 today. And what are the thoughts on this one? Sorry, let me bring it back. Here. Are you able to hear me?
Yeah, I'm just still thinking about it.
Okay, no problem. Also, feel free to think out loud. We're just in the process of discussion, so feel free we can think together on this question.
I was kind of thinking that it would be the less massive one, because if they were like already moving and they were moving with the same direction and speed, but the less massive one would have like it's kind of like what we were learning about momentum and stuff, and it's easier to I guess slow down or stop because it has less mass.
Mhm. I see. So you're thinking the less massive object is easier to slow down, right?
Yeah.
Or speed up. Okay, that's a very good intuition. But there's another intuition that that's kind of a conflicting the thought is the less massive one will also require less force to speed up or slow down. So let's think about, in this case, what is a force that is providing that acceleration for them to slow down?
It would be the friction from the brakes, right?
Yes, it's the friction. So you have a friction acting on both of them. Has a friction. So both of them has a friction. So let's see how much that friction is. Friction is equal to mu k times what? You still remember how to calculate kinetic friction?
Times the normal force.
Yes, times the normal force. So if we're talking about the green car, the M, the less massive one, the normal force is going to be weight equal to the weight of that car, mg. If I'm doing the kinetic friction on the orange one, the more massive car, you can see the friction is going to mu k times a bigger normal force, that's 2 mg. So yes, this one does have, is easier to slow down, but it does not have as much force to slow down. This is because it is doing the sliding, okay? So the force that you provide to both of the cars are actually different. And let's see, if you apply this force to the two different objects, and each of them will be given a acceleration, right? So you will give an acceleration to this car, you'll give an acceleration to this car. So now I convert the question to the kinematics question is which vehicle stops first, is which one has a bigger acceleration. Because if you have a bigger acceleration, that takes less time for your velocity to be reduced to 0. So that the sort of a alternative question is which one has a bigger acceleration. I'm actually going to stop here because our next question is asking and changing this problem to which one has a bigger acceleration. You may already know the answer, but we will talk about the final process later. Okay, I'll see you guys in a bit, okay? Oops, sorry. All right, as you come back from the breakout rooms, please put in your vote. We will go for another 10 seconds. All right, any last minute vote? Okay, then I'm going to end the poll and we'll take a look at the results. It looks like we're almost tied. Well, slightly more voted for both stop at the same time, and the next popular answer would be the less massive one. All right, very good. Okay, so anybody would like to give some thoughts? It doesn't have to be a final conclusion or just any intuition that may help us to process this question.
One thing I kind of remember from driver's ed was that they told us that when you're driving on like the freeway, as the faster you go, the longer it takes to brake to zero. So that's why you have to like maintain like the 8 to 10 car distance or whatever.
Mm-hmm.
And I remember them saying something like it didn't really matter how big your car was for most purposes. At least that's how they framed it. So then I selected both stop at the same time because after thinking about that, I set up the physics equations and I got F of M, which is just the smaller mass, is equal to MA minus mu of K N of M. And I don't know if that's right. So then for the next one, I did F of 2M and it's just 2 times MA minus 2 times mu of K normal force, because the normal force is just like twice as much force in each of the components because it's twice the mass. And then I got it to 2 F of the smaller one is equal to the F of 2M. So if you get both equations to be 0, MA, like they both, I think, reach 0 at the same level of acceleration when you plug it in. I think. So that's how I did it. I don't know if that's right though.
That's excellent. Before we go to look at the equations, I want to ask a follow-up question on the driver ed, that information you were told. They were saying it doesn't really matter how big your car is it as a persuasion, thinking that, oh, even if you're driving a smaller car, you still need to give yourself enough stopping distance? Is that what they're trying to get at? Because we know bigger trucks definitely need a longer stopping distance.
Yeah, they said it was because of the end. Obviously, I didn't really look into it much after that, but they just said it was because like normal cars, they said like even if it's like a lot bigger, but it's still like a normal 4-wheel car, it'll be pretty much the same. But they said that the bigger trucks, because of the engines and like how long the car is, I don't know, man. That's just what they said. So they could have been doing that to persuade us.
Okay, the lesson, I don't want to be you taking the lesson from this question and don't allow yourself enough stopping distance when you're driving a car, especially a truck. Okay, the reason is here we did in an idealization, we're saying, assuming these cars are sliding. Okay, so we're relying 100% on the kinetic frictional force to stop. And that is not the same how your real vehicle works. Here, real vehicle is more like you're providing a force, a stopping force. Let's say if you're giving 2 cars the same stopping force, then the bigger or more massive ones will have a smaller acceleration. It'll take longer to stop. That's what happens to the bigger truck. The oversized engines, even though the trucks may provide a bigger stopping force, but it's not like how we are doing it here, where you can see that. Yeah, so now we can rely on the equations to sort of sort out this intuition that even though the more massive cars is harder to stop, okay, 2M, it also generated, because of its own weight, it generated more force. This sliding frictional force is generated. So you can see the M cancels out and give me the same acceleration for both of them. They both have the same acceleration for mu k g. Okay, that is when under the assumption they are sliding. In real life, it's not quite that. So definitely need a longer distance for a bigger truck. Okay. So as far as this one, yes. So if they have the same acceleration, it takes them the same amount of time to stop. Okay, so they both stop at the same time. So we kind of did two questions together because to answer, you can see to answer this question, which one takes longer is a sort of, I changed to another question. Well, that's a kinematics question, which one has a bigger acceleration? And using dynamics, Newton's second law we just did, you figure out A1 and A2 are the same. So they take the same amount of time to stop. Okay. So if I change the problem to, you have two different massive objects and you give them a push, the same amount of push, then do they go the same distance?
They don't, because your
No.
your force is only going to get so far.
Right, the ones, because now the force is the same, the one that's less massive are gonna have a bigger acceleration. So that again will be different from the one that we're looking at here. Here, the force is also bigger because of the bigger mass and the normal force that it generated. Okay, very good. So the answer is yes, they will both actually stop at the same time. This is also very similar to when we have free fall. We have different size, different objects with different masses. You let them go and they drop to the ground. We said that the experiment that Galileo did and he performed, because the more massive ones have a bigger gravity. However, it is also harder to change the acceleration to speed up the more massive one. So those two influences kind of cancel out from each other, just like how we cancel out the m from the equations. So they end up falling at the same rate. So this is exactly the same as free fall, but just in the horizontal direction. Let's look at a question, sort of a problem where we utilize both kinematics and the dynamics we just learned. So we have a car with the mass m is sliding down to a stop. So originally it has a velocity going down on the hill, and you have a small angle, that is the angle of the ramp. The kinetic coefficient is giving us, and it is sliding down, but it is sliding down to a stop. So meaning that it's actually slowing down, right? Eventually it stop. And we want to find the normal force acting on the car. We want to find the kinetic friction acting on the car. Those are two smaller questions, but further, we want to be able to answer how far does it take for the car, how far would it slide before it stops? So that is a kinematics question. We're looking for the distance, right? Okay, but through the first three questions, we can finally get to the last question. All right, so quickly, if you have your notes in front of you, please draw the free body diagram of the car. So let's draw the free body diagram together. First of all, I'm going to draw gravity. Perpendicular straight downward. And then I'm going to draw normal force. It's perpendicular to the surface upward. And then I'm going to draw friction. So which way is a kinetic friction? It is moving, so it has kinetic friction, not static friction. And is pointing down the ramp or up along the ramp?
It's beneath it, right?
I'm sorry.
Oh, is the friction beneath it? Or
Yeah.
no?
Yes.
Okay.
Mhm. Friction is, should I draw it this way or this way? Thank you, Rosali.
To the left,
Oh, yeah, left. Yeah.
to the left because friction opposes the direction.
Yes, very good. Thank you so much. Yes, we're going down. So it's opposing the velocity, which is upward. Excellent. Okay, so now let me also set up my X and Y directions. Okay, so I set it up like this. And velocity is going down, friction is up. What about my acceleration? The car's acceleration is along positive X or negative X?
Negative X, because it's going towards the origin from the positive side.
So is my acceleration going down the ramp? Or is my acceleration going up the ramp?
It's going
Given
down.
my- Given my velocity is going down the ramp. So my velocity going down because the car is sliding down. So that tells you velocity is going down. But is my acceleration also pointing down?
It's not, because you're slowing down. Yeah.
Yeah, it's slowing down. Excellent. So we know the acceleration is going to be in this direction. It's slowing down, coming to a stop. So acceleration is opposing the velocity. So you can see before I set up my equations, I need to make sure I have all my quantities labeled correctly. All right.
For this,
Yeah, go ahead.
For this problem, why did you have X go like to our left instead of to the right, like usual?
Because I usually like to have my acceleration in the positive direction. You
Okay.
don't have to choose it that way. You can choose the other way around. Do you wish me to reverse it?
No, it's fine. I was just wondering why you did it that way.
Yeah, it's totally up to you. I can even reverse my Y to be downward. That will not change your result. You can try after class to reverse your X to see how it works out. Okay, so now I have all my forces. My force of gravity, I always want to decompose it into two different forces. One is FGY, one is the FGX, okay? But after I draw these two forces, I crossed out my gravity, showing that I have already considered gravity, okay? All right, so I have all my forces now. So we're ready to apply Newton's second law. First of all, to find normal force, we know, well, that is something we have done multiple times. We just need to apply Newton's second law in the Y direction. So there are only two forces in the Y. At this point, anybody could simply say out right away what the normal force is going to be. Hopefully, after a few incline problems, we're already very familiar with it. So the normal force is going to be equal to what?
FG cosine theta, I believe.
mg cosine theta. Excellent. So this is theta. This little angle is theta, the same as this theta. Okay. All right. So to set it up, you actually have normal force in positive Y, FGY in negative Y, so normal force minus, and zero acceleration in the Y direction, giving you normal force is equal to this component of gravity, which is mg cosine theta. Okay, so that's all we need at this point. Don't plug in numbers until the very end. It's not asking for numbers. So question 2, what is the magnitude of kinetic friction? Kinetic friction is mu k times normal force. We already know that. And you already found normal force. So plug it in, it's going to be mu k mg cosine theta, and that's it. That's our second question. All right, I'm going to move on to the third question to calculate the acceleration. Before I do, any questions here? Any other questions about what we have done so far?
Could you briefly go over the mg cosine data in terms of use of k?
Yes, so that is from looking at the geometry of the angle. I know that this is FGY, this is FG, this is theta. So in this triangle, this is cosine theta is FGY over FG. Does that make sense?
Okay, gotcha. Yeah, thank you.
Very good. Now this is just a little bit careful. If you know this is, for example, 30 degrees, you know this is 60, you know this is 60, and you know this is 30. So if you draw it carefully, you can see that. But once you've done it once, you can just write it down right away. You don't have to derive it. Okay, thank you for asking. And the third question is, what is the magnitude and direction of the acceleration of the car? Okay, that is asking acceleration in the x direction. So let me go back and I want to refer to my picture here. To find the acceleration, we need to set up Newton's second law in the x direction. So all the forces in the x direction, there are really just two forces. One is FGX, one is friction. Now let's just decide which one is positive, which one is negative. My x is pointing along the ramp, so my friction is also in that direction, so that's positive. But f of gx in the opposite direction, that is so that is going to be negative. And it's equal to ma. A is in the x direction. I have a question here. Is the friction also equal to the opposite of the horizontal component of gravity? Yeah, so you're asking about the question 3 here. If the car has no acceleration along the ramp, you can see that if the car has no acceleration along the ramp, then yes, friction will equal to the component of gravity. But in this case, the car does have an acceleration, so the friction will not equal to the component of gravity. And in fact, we will calculate how big the acceleration is. And acceleration is up the ramp is positive. If you had defined your downward to be positive, then you would have added a negative sign here. But since I have already said that is positive, I just say n times a. Okay, so let's plug in all of these two components. The other component, gravity, is mg sine theta, right? And friction, you already know, is mu k mg cosine theta from question number 2. So you can plug in everything. So you can see why I encourage you to wait until the very end to plug in numbers, because here, for example, the mass cancel out. You don't really need the mass. It doesn't even give you the numbers. You didn't really need the mass. So you found the acceleration to be mu k g cosine theta minus g sine theta. Or if you wanted to group it a little bit more, you can say, oh, it's going to be g mu k cosine theta minus sine theta. So that is third question. That is your acceleration. Any questions about what I did here? Any questions? Sorry, when to jumped. Okay, so you can plug in numbers, 9.8 meters per second square, μ of k, what is μ of k? 0.1, cosine 5 degrees minus sine 5 degrees. So you calculate it and you get it's a quite small acceleration. That is your acceleration. So that's my question 3. Last question is the kinematics. You can see so far we've been working with Newton's second law, but having the acceleration sort of the bridge between kinematics and dynamics. So now we can find out how far does it take for the car to come to a stop. So this last question is kinematics And think about physics, right? Think about what physics we have. We have a motion that is constant acceleration. And there are some equations we use for constant acceleration. What are they? It looks like this. Another one looks like this. Another one looks like this, which is not a new equation, but just can be derived from the previous two. So we have all these set of equations, and let's choose the one that's more relevant or more easier to use in this case. So we found our acceleration. We are given initial velocity. We know it comes to a stop. So we want to find the distance. So I'm going to choose the third equation, right? That seems more straightforward to use right now. So I'm going to choose this equation, and I can plug in the numbers. You can plug in, okay, final velocity is 0. Here, be very careful with your signs. Okay, initial velocity is -10 because it's opposite to what I defined to be positive. But it end up to be, doesn't really matter because you have squared. And also you can see here I'm going along the ramp is where my x is increasing. So if I have my x initial here, my x final is here, okay, because that is you're originally to the left of where you are, and you end up to be here on the right hand side. So here your x initial is bigger than x final, which make x final minus x initial to be negative of the total distance you traveled. Okay, so now you can see, all right, and that works out. I found my distance to be 10 squared divided by 2a, and I found the distance is 4. It's a really long ramp, I guess, 400 meters. Okay. All right, so you can see probably the way how I calculated kinematics, it showed me maybe it would have been easier if I had chosen down the ramp to be my positive direction. So my delta x is positive. Maybe that would have been easier, and acceleration would be negative. So, but it's good to see different variety of ways to do that. So you can choose whichever coordinates you like. All right, so that is a question that uses both Newton's second law and kinematics equations combined to solve problems. Okay.
I was a little confused. Are you able to scroll up a little bit?
Yeah.
I was a little confused by negative FG earlier. Plus I think it's going up a little bit more. I was a little confused by that part. Negative FG plus F of K.
Oh, it's really just which force is pointing in my positive direction. F of K, my positive direction is up the ramp. So F of K is in that direction. F of GX is down the ramp, which is opposite to what I define to be a positive direction. That's why this is negative, this is positive.
Oh, how come F of GX doesn't have mu mg sine theta? Is it because it's not a frictional force?
Yes, it's not a frictional force. Only friction has that mu sub k in it. F of gx is mg sine theta purely from geometry.
Oh, okay. Is that just like the force of gravity in the x direction, or?
That's the component of the gravity you get when you're on the ramp. That is the force that is responsible for you to go down the ramp.
Okay, thank you so much.
Of course. Thank you for that question. So this is one example with kinematics and dynamics. Let's move on. Next, let's look at, this is, okay, so this is a question where you have something on the box, a box sitting on a horizontal table, and you have a tension that's being applied to the box, but static friction is stopping the box from moving. So it's kind of like the one we did in the lab where you pull the cart, but except we're not really looking at the hanging mass part right now. You just have a tension. Wherever the tension comes from, we don't really care. We just know that is T applied to the box. Okay, so what is the magnitude of the total force acting on the box? This one we don't need to discuss. It should be fairly straightforward. So I will just go ahead and let you put your thoughts here in the vote. Yeah. Sorry, this is M. It's supposed to be mu. Okay. All right, 10 more seconds. If you haven't voted already, please do so. All right, any more thoughts, more votes? Okay, let me go ahead and stop it. All right, so let's look at A and B, which is sort of tied for a second popular answer is mg. Well, mg is the weight of this box, right? A mu mg. Now, if we're using static frictional coefficient, that gives us the maximum static friction the table can provide. But are those questions what is being asked? It's asking for the magnitude of the total force. So you might wonder, okay, how do I find the total force? Which means all the forces. Oh, there's a lot. There's mg, there's a normal force, there's tension, there is friction. How do I know that what they add up to? Anybody?
I think we know that they add up to be 0 because of the fact that we're saying it still stops, like it never starts moving, it stays at rest. So I kind of just did like, I used my positive x direction in the direction of t. So I did t plus f equals 0 and t equals f, like the magnitudes. So that's how I figured it out.
Ah, very good. So a very key information in there is sometimes don't get too swamped into the details of the forces. Here it's at rest, which means acceleration is 0. We don't even have to calculate the t because the sum of the forces is ma. It's going to be 0. This is total force, right? That is exactly what is asking. What is the total force? So right away, very key information is whenever the problem says something is at rest or moving with a constant velocity, both of those situations you have 0 acceleration, and both of those situations you know the net or the total force is 0. Okay, you don't have to think about the details of how they add up. So the answer is it is 0. So this is a bridge question you have done. It's asking about the static frictional force. Now we know that That's something that one had just talked about. If you do apply Newton's second law in the horizontal direction, then you can figure out the static friction. One is the tension, one is the static friction preventing it from having an acceleration. So this is 0. Your static friction is equal to the tension. Okay, so that's answer is C. Next question involves again multiple objects. Okay, slightly different from what we did in our previous class. Now you have two different masses, M1, M2. M1 is bigger, M2 is smaller, and you apply the same amount of force. So here, assuming the net force you applied on the box is F. Okay, you don't have to think about, oh, are there any other forces? It's just F. F is it. Whether you push it from the left-hand side or you can push them from the right-hand side. In which of the two cases is the contact force between the two boxes larger? Contact force, meaning, what do I mean by contact force? Meaning that there must be a force pushing M1, and that force is coming from M2. In this case, case B, there is a force pushing on M2, and that is coming from M1. Okay, so that's what I mean, contact force. So let's think about how do we figure out which of the contact force is bigger, or maybe they're the same. All right, so take a screenshot of this if you want to just discuss a little bit, and after we come back, we will work on this question together. And I will visit the room 8 for breakout rooms for this question. All right, how's everyone doing today? Again, I'm not looking for an answer already, just here for the discussion. Anybody have some thoughts of how to go about this? Like, where do we start?
I'm not too sure yet. I'm still thinking about it.
So it's asking about a force. Perhaps Newton's second law can help us. Would you agree that maybe we can use Newton's second law?
Yeah,
Yeah.
what I have on paper right now is F equals M2 plus M1 quantity times acceleration.
Okay, let's do that together, shall we? So you said for case A, you wrote down this force, the entire force is applied on two of the objects together. So you have something like that, right?
Yes.
Okay. Everybody agree? That looks good?
Yeah, that makes sense.
Okay. So let's do that for case 2. Why don't we do that? So case 2, it's not going to be anything different. I have the same force, and again, I'm pushing both of them. So I have the same information. So which really just going to be, so I'm going to say case A and B give us the same information that the acceleration is equal to F over M1 plus M2. Okay, what should I do next? This is giving me an overall acceleration of M1, M2. Do you think M1 and M2 have the same acceleration?
No, they don't. Like individually?
Yeah, individual. They're together. They're part of the whole.
So if it was individually, then the M1 would have a smaller acceleration and M2 would have a bigger acceleration.
Okay, sorry. I think what I asked was confusing. I don't mean individually as you pushing them individually, as I mean, if I'm asking in the case of scenario when M1, M2 are still together, do they have the same acceleration?
Yeah, they do.
They should, yeah.
Very good. If not, they're gonna be falling off.
Because
Very
they wait.
good. So what do you think the next step would be? If I want to ask a contact force on one of them, should I isolate that object? Meaning that you focus your attention on M1 or you focus your attention on M2. You do the analysis separately. Does that make sense?
Okay.
Yeah, so if we focus our attention on M1, oh, I realized that I gotta go back. Let's finish this together because everybody else needs to hear this too. So let's go back and then I'll work out the rest with the whole class. I realize we only have a few minutes left, okay? All right, I'll see you guys in a little bit.
Okay.
Bye, Professor.
Okay, sorry, I was just looking for the button. All right, we have a couple minutes left. So just going to, let's work on this together as a whole group, okay? I'll just wait for everybody to come back from their breakout rooms and we can work on it together. But you still feel free to put in your vote anytime you feel like. All right, just a few, 15 more seconds and everybody should be back. Okay. All right, so let's work on this together. You can still vote, put in your vote if you like. I'm going to, first of all, do a Newton's second law application on 1 and 2 together. And I realize for case 1 and B that they're exactly the same. You have the same force applied on both objects, so you give you the acceleration in both cases the same. Very good. But the question is asking the contact force between the two boxes. So if I want a contact force on M2, on M1, from 2, it makes sense for me to focus all my attention on M1 and do a Newton's second law analysis on that one object. So this is what I'm going to do next. I know to get the contact force on M2, I need to apply Newton's second law on M2 or M1, which means that this force on M1 provided that acceleration because 1 and 2 should have the same acceleration. They're moving together. So F21, I can actually calculate this contact force is M1 times F over M1 plus M2. I got it. Now I do the same thing for case B. There is a contact force from 1 acting onto 2, pushing M2 forward. And if I do Newton's second law, for that force, I will get very similar to case A. I will get F1, 2 is pushing on M2 and giving it that acceleration. That acceleration is the same, is F over M1 plus M2. So this is case A, this is case B. You can see that they're not the same. Okay, case A, we have F over M1 plus M2 times M1. Case B, you have F over M1 plus M2 times M2. M1 and M2, M1 is bigger. This is the same for both. This is bigger. So case A is bigger, right? Which means the answer is A. Contact force A is actually bigger between the two objects. This is quite interesting because you think, well, I'm just pushing both of them together, but which one you push on actually made a difference in their contact forces. But you can always figure it out by isolating that object and do a free body diagram on that object alone. All right, so that's all for today. I'll upload my lecture notes and video as soon as I could. And have a good weekend. I'll see you guys next week.
Thank you. Have a nice day, Professor.
Thank you. Bye, everyone.
Bye, Professor. Have a good day.
I want to let you know the practice exam solution is now posted. So if you haven't done it, make sure you do it next week, and because our midterm is a week after. All right, see. Bye, everyone.
Bye.
Professor,
Yes.
could you scroll down a little bit? I had a question on
Yes.
that
So
particular problem.
this here.
Yeah.
Okay.
So I'm a little bit confused on why it would be on the A value. So I know that you did M of 2. Wait. Oh, I got it. Oh, I got it because A is equal to, is proportional to F over M1 plus M2.
It is the same for both. You could
Yeah.
have just replaced the whole thing with just A, and not the
Okay.
and that would maybe easier to look at.
Yeah. Okay. I was just confused by the mathematical aspect because the way I kind of saw it was thinking like more in terms of like, okay, if you have like a large, if you're applying friction and you have a larger force, a larger mass pushing on a lighter mass, it's more likely for that force to be much more grand than a smaller force pushing on a larger force. So that's why I was kind of confused on if that makes sense.
Yeah, but then whether the mass is big or not, the mass itself doesn't do anything. It's really the force you are providing to both of them together. So I would say that intuition is not very helpful here because, yeah, why would because a small mass can exert a big force. You just have to push harder, right?
Oh, right, because
Not much
the
to
total.
do with a mass.
Okay.
Right. Yeah, it's not like you have the weight of them, one sitting on another. So it's really, you know, you can still make it push harder if you want. So yeah, it's a good intuition. It's not very very relevant or very useful here in this case. So when we are confused with our intuition, we can always rely on looking at the physics and try to isolate the problem.
Oh, also, wait, sorry, Professor. Right before I left, you mentioned something you said something right before I left. My bad. I missed that for a second, so I just came back. You said you wanted something.
Before I left the breakout room.
Oh no, before like we left, like before I said goodbye, you said you want.
Oh, I want you to make sure you do the practice exam before the actual midterm.
Oh yeah, definitely.
Yeah.
Is the practice exam similar to the midterm, by the way?
Similar, I mean, which is similar. All problems look similar to me because if it's a Newton's second law problem, it's similar to me.
Okay, I see. I just meant in terms of difficulty of the problem.
Difficulty similar, yes. Yes, that the answer is yes to that.
Okay. Yeah, I'll do a lot of reviewing. I'm struggling a little bit understanding like a lot because there was a lot of different frictional or like different forces and a lot of different things to comprehend in this. So I'll take a lot of time to study this weekend and ask more questions next week.
Yeah, absolutely.
Yeah, thank you, Professor. Have a nice day.
Yes, thank you. Have a good day. Bye-bye.
Yeah, I'm pretty scared too. So yeah, so yeah, in terms of what I was saying, so overall, a smaller force can obtain a larger force by a larger push on it, right? And in terms of this particular problem, since we have the total mass remains the same for both trials, is that what you were kind of trying to say? Since the total mass remains the same for both trials, we're kind of looking at the more mathematical approach.
Yeah, the total mass is the same for A and B, and so they have the same acceleration. The contact force really just depend on this contact force is provided such an acceleration for which masses. If you want to be able to push on M1, which is a bigger object with that acceleration, you need a bigger contact force. So basically.
Okay. Okay, thank you, Professor.
Thank you. Bye-bye.
Bye-bye.